Hello, welcome to my channel. My name is Maxwell Momanyi Omanga, and I shall go through the Introduction to Algorithms Assignment Solutions. The first question is, show that the solution Tn to Tn minus 1 plus n is big O n. Therefore, let us assume that Tn is less or equal to Cn squared, n greater or equal to n naught, where C and n naught are positive constants. Therefore, let's plug in our assumption into the equation, and we have the Cn squared, C into brackets n minus 1 squared plus n. Then Cn squared, as you expand this, you find Cn squared minus 2Cn plus n. Let us assume that n equals to 1. Then therefore we're able to get this equation, concluding that. Then eventually we come to the end and we say that n Tn is less or equal to n squared, and this holds as long as n is greater than 1. Here we have a little table showing us how the behavior goes on as n increases. As you can see, when n is 1, Tn minus 1 plus n is equal with n squared. But when n is 2, we see the condition is satisfied that Tn minus 1 is less than n squared. As you can see, the values, the Tn is less or equal to n squared. The next question is saying you're having a recurrence equation. We are going to use master theorem to give the tight asymptotic bound for the following recurrences. T of n equals to 2t and brackets n divided by 4 plus square root of n. We know our a equals to 2, b equals to 4, and fn equals to square root of n. There we see now, if you substitute in our n to the power log a base b, we substitute in our a and b, and we find that n to the power a half. Then you compare now the value we've got here with the fn, and we discover that this value is n to a half is equal to a square root of n. And since they are polynomially equal, n to the power half is polynomially equal to f of n, it has the behavior of a constant series. Therefore, that gives us, that is case 2 of master theorem. And at this point, we shall plug in the term complexity of case 2, which is theta n to the power n to the power n, theta n to the power log a plus b. We plug in the time complexity of case 2, which is now our final answer will be theta n, theta square root of n log n. Our second recurrence equation is we were to test the same equation but using substitution method. I tried this out, and this is my solution. So again, we check if this we show that the solution for this recurrence is theta square root n log n. So Tn is less or equal to Cn, and I plug in into the equation. I'm having this, then I expand that, to expand this will be 2 to cancel out with that. Then when you expand this, we're able to find this equation. Let's go down and we find again the condition it would be satisfied. This is true when c equals to 1 and n is greater than 4. And this is how the figures behave when you plug them in. You see that we have when n is 1, n square root of n log n is 0, which is greater than this. This condition is not satisfied. Even here it is not satisfied, but even this one is not satisfied. Then beyond 4 is when we find that the condition that Tn is less than square root of n of log n is satisfied. So n greater than 4 onwards will be able to satisfy by substitution method. Okay, let's move on to the next question. We have t of n equals to the 2t. Is also an recurrency question. 2t n divided by 2 n to the power 4. Our a is 2 and our b is 2 and our f of n is n to the power 4. You plug in into our equation here and you can see log 2 base 2 give it what we want. Now we compare n with f of n. We find that n is less than n to the power 4. Since n is polynomially smaller than fn, it is in a decreasing geometric series, which gives us a hint that we need to have to add some small value in power here to be able to make it, and that epsilon, or that epsilon to be added, will be 3, hence case 3 of Master theorem. Therefore, we come here and we now check with the regularity equation, and we see that f n divided by b are equal to c f n. I'll be able to come up with this equation: c n divided by 2 log n divided by 2. How we come up with this is, you know that when you have a f n minus b is the same as a n divided by b multiplied by log n divided by b. So this is a expansion that we are using to be able to come up with this. And I find that if you plug in any values of n here, any positive values of n, they will always be less or equal to c n cubed to the power 4. That means this condition is also satisfied. Therefore, the time complexity for case 3 will be theta fn, and for this case it will be theta n to the power 4. Then we go to another equivalence equation: tn 7t into brackets n divided by 3 plus n squared. Our a is 7, our b is 3, our f of n is n squared. Therefore, if we plug in into the equation of n log to the power log a of b, we find this equation, we find this result. We compare that result with the fn. You find again is polynomially smaller than the f of n which is a decreasing geometric series. Case 3 and our epsilon here will be approximately 1.3. Is case 3 master theorem. Once again, when you plug in the regularity condition, you would see that still when you use this, check this condition is always satisfied that it will always be A F n divided by B will always be less than equal to F C F of n. For some C less than from 0 less than C less than 1. Therefore, time complexity will be theta n squared. Another recurrency question. T of n equals to 2t n divided by 4 plus n squared plus square n. Our A is 2, our B is 4. Plugging into the n log B, A of B, log A plus B. We find that solution, compare that solution with the function, and if we find the polynomially equal, hence a constant series, which is the case 2 of master theorem, and therefore if we plug in our time complexity equals to theta square root n log n. Then finally 3a, 4.3a, Tn equals to 40 into brackets 3 divided by n divided by 3 plus n log n. Our A equals to 4, our B equals to 3, and our f of n equals to n log n. Plug in the A and B respectively, and you get this solution. That solution, we're able to, that result, we're able to compare it with the Fn, and we find that n to the power 1.2618 is greater than n log n. Therefore, since n to the power 1.2618 is polynomially greater than f of n, which is an increasing geometric series, we'll be able to take the form of case, to be able to take case 1 of master theorem, where we shall need to subtract some epsilon for approximately 0.2 from the equation, and therefore our time complexity will be theta n to the power 4 to the power log 4 base 3, and that is it gives us the asymptotic bound, in this case upper bound, gives us the asymptotic upper bound for this equation, which is theta n to the power log 4 base 3. Thank you very much. See you next time.